This is my NASA internship by me, Lillian Hall, and my mentor, Juan Carlos Martinez Oliveros. What is an eclipse? A solar eclipse is when a planet's moon passes between the planet and the sun, casting a shadow partially or fully blocking out the sun's light. Facts about eclipses on other planets. Jupiter has large moons, making solar eclipses common. When Saturn's natural satellites pass in front of the sun, solar eclipses may happen. Mars has two small satellites that barely make an eclipse but can cast a partial shadow while blocking out the sun. Solar eclipses can happen in numerous exoplanets outside of our solar system, and eclipses cannot occur on Mercury or Venus due to lacking the natural satellites. Partial versus total eclipse. Total eclipses can only be seen from a certain site and last a couple of minutes, making it difficult to track the time variation of the corona. Partial eclipses are easier to study because it can be viewed from several places. Partial eclipses are long, and several scientists gather to record the time variation of the corona changes. Total eclipses last 10 seconds to 7.5 minutes. And then I read an article about solar coronal and polar jets observed during the 2017 solar eclipse. They were initially observed in polar coronal hole regions, studied with soft X-ray and extreme ultraviolet. Jets can escape from the sun in the solar wind, but the EUV and soft X-ray emission cannot be seen at larger distances. Several highly energetic jets have been proven to reach high altitudes, while smaller jets are not confirmed to reach such altitudes because of poor detection. The data gained from the solar eclipse was able to investigate the unseen behaviors of polar jets above the heights. And these were the scientific claims about the several jets. Polar jets contribute to polar solar wind. Energetic polar jets may escape the sun, while ordinary ones are less likely to. Some studies show that jets do not escape from the sun, they fall back to the solar surface. Standard jets cannot be seen in the images taken with SOHO, LASCO/Core 1, but blowout jets are seen. Blowout jets have larger widths than standard ones. And lastly, one claimed that the reason that the ultimate height of jets is not very clear is the limitations of height coverage in observations of the corona. And here are some images of the blowout, polar, and other type of solar jets in the sun. And then the Eclipse Mega Movie. The 2017 Eclipse Mega Movie was an opportunity that arose for people in the US to capture images of the total solar eclipse to align a movie of changes in the solar corona. Over 2,000 people submitted photos with a total of 50,000 images captured. The Mega Movie scientists gathered, aligned, and processed the images to create high dynamic range images for the purpose of studying the solar corona. With the success of the 2017 Mega Movie, the 2024 Total Solar Eclipse Mega Movie is now in process. Now my project, The Goal. The Eclipse Mega Movie in 2017 and 2024 include images taken without professional equipment. Because most of the photographers did not use tracking mounts, the moon and the suns move in time within the field of view. To reduce the data, the following steps were taken: aligning and recentering the images of the 2017 solar eclipse data using Python, processing the resulting images with the histogram equalization algorithm, and finding solar jets and flows in the solar eclipse data, which is ongoing. Now I'm going to get into the steps of image alignment. Image conversion and preparation. The images provided by the Mega Movie, volunteers were uploaded in the native camera raw format. That is a binary file with non-compressed data and all camera metadata. In Python, using the model ROPI, the images were uploaded. To convert the images and prepare them for further processing, the following was made: converting images Python objects to NumPy arrays. Convert NumPy arrays to grayscale. With this, we changed the images from a 3-color multi-dimensional array to a 2D array, which is easier to manipulate. ECC algorithm setup. The Enhanced Correlation Coefficient ECC image alignment algorithm estimates the geometric transformation between the input and the template image as it returns the warped input image, which must be close to the template one, as it is shown below. The estimated transformation is the one that maximizes the correlation coefficient between the template and the warped input image. In our code, we define the motion model, initialized warp matrix as an identity matrix, and specified the parameters for algorithm. And then the image alignment step. Apply ECC algorithm to align image 2 gray with image 1 gray, and use CV2 warp affine to apply warp matrix to image 2 gray, producing image 2 aligned. And then computing and visualizing image difference. We implemented a code routine to highlight the difference between image 1 gray original and image 2 aligned by computing pixel differences. Here we can see the apparent motion of the image center and when possible its rotation. We highlighted the difference between the aligned image and the preceding aligned image. Since the sample data set from one station, no changes will be visible and therefore this box will be empty. And here's a picture of the aligned images, and as you can see, the aligned image was converted to grayscale and was centered. And then image histogram equalization. Histogram equalization adjusts the intensities of the image so that the histogram of the output image is approximately flat. This enhances the contrast of the image. Filamentary structures in the solar corona are faint, and using imaging techniques like histogram equalizations help to detect changes in the coronal structures. And then lastly, we transformed the polar coordinates. To better study the sun's coronal structures, we transformed our eclipse images XY coordinate to radius angle coordinates. This conversion allowed us to analyze radial variations, study changes in coronal brightness and structure as a function of distance from the sun. It identifies symmetrical features, easily detect and quantify features with rotational symmetry, such as coronal streamers. It enhanced visualization, creating a visually striking polar plot that highlighted coronal details. And here's an example, and as you can see, it highlighted the coronal structures, which makes it easier to detect the changes. Thank you.